Okay, so this is a mixed analysis of variance, to a mixed ANOVA. And in a mixed ANOVA, we have a combination of within and between participant design. This is the simplest one you can probably have. So what we've got here is basically we've got psychology students and engineering students, and we're looking at whether the different kinds of students are quicker or slower at recognizing particular shapes that are presented in a heavily degraded, heavily noisy background. So if you're given these shapes, they're quite difficult to see, and we're simply measuring how many shapes on average each person is able to recognize. So the bigger the number, the more shapes they've recognized, so the better the number is. And for some reason, the researcher decided to see whether psychology students and engineers differ in this ability. So within subject design, all participants are given the rectangle and also the oval. So they're given a combination of rectangles and ovals, so everybody has the same stimuli. So these are done simply as columns, which is how you set up the levels of a single variable when it's a within subjects variable. These columns are not variables in this case. These columns are levels of a variable. The variable is shape, 2 levels. Profession has 2 levels, so again it's another 2x2 design, just like the between subjects ANOVA and the within subjects ANOVA, but in this case there's a between and a within variable. The between subjects variable is obviously profession, because somebody's either a psychology student or an engineering student, not both. So again, if we take each row as a person and each column as a measurement of that person, then we can see person 1 has the attribute psychology student and their scores for the respective shapes there. So it's relatively straightforward, and as before, you would do the usual test for outliers first, then tests for skewness to make sure the data are permissible to be used in ANOVA, that they're not skewed, and if they were, you'd have to sort out any outliers or any skewness before you could do an analysis of variance. The scores themselves are ratio scale because it's simply how many shapes you manage to correctly spot. So the maximum is 0, and the maximum is whatever the maximum is, 10 or 20. The minimum is 0, right? And so it's a ratio scale. So we would have tested for skewness. Everything's okay. We know that we can now use an ANOVA where we can use means, we can use standard deviations because the data meet parametric assumptions. So let's get on and do the ANOVA. As usual, we found the ANOVA for univariate where you've got more than one IV, and in this case we've got more than one IV, we've got 2, is in GLM, General Linear Models, and as before we want repeated measures. Okay, univariate here, which we've used before for between subjects, is only good for between subject factors, whereas with repeated measures you can actually put a between subject factor and a within as well. In fact, you can put more than one between, more than one within. It can get quite complicated entering the data if you have more than one within subjects variable paired with a between subjects variable, as we saw when we did the within participants ANOVA. You have to make sure that the variables match up to the numbers in the box on the next screen. If you've not seen that one, I suggest you look at the other 2 ANOVA screencasts before you look at this one, because this really is a combination of the 2. So factor 1, this is our within subjects factor. So this is shape. And shape has 2 levels, rectangle and oval. We don't need to tell it what they are. It would be nice if it could tell us this, but there we go. And that allows us, that's our within subjects variable added, and then we go to define. Now we've only got one within subjects variable, so this is much easier. So rectangle and oval are the levels of this variable, and in the box here we've got a simplified version of what we saw in the within subjects ANOVA. If you remember, in that one we had the number of each variable was the ordinal position. So 1, 2 was level 1 of variable 1, and the 2 was level 2 of variable 2. All kind of a bit confusing. If you're confused now, go back to that screencast and watch it again. I'm confusing myself, so I'll carry on. So let's just say in this case, rectangles are 1, and we'll have to remember that for the moment. You'll see why. Rectangles are 1 and ovals are 2. Okay. Right, okay, so profession is our between subjects factor, so we just put that in there. That's all set up, ready to run. We will get some plots, very important. I can't stress strongly enough how important it is to get plots, and do like I always do and get the plots both ways round. So we've got profession by shape, and then we'll also do shape by profession, because some graphs are easier to interpret than others, and you can never at this stage know which graph is going to be the easiest one to read. So do both, have a look at them, which one makes most sense to you. Very important, that. Okay, so let's go continue on that. We want to take some options, so we can have descriptive statistics if we want, so we can get it to display means for everything, the profession and shape for your descriptive statistics section. We can have estimates of effect size. We can have power if we want. I'm not terribly interested in that, but some people love it. Homogeneity tests, again, one of the assumptions of ANOVA is that the variation in each of the groups is approximately the same as the other groups, that one of the groups hasn't got a massive standard deviation or variance and the other one smaller. If that happens, then we might have to adjust the ANOVA. So that's all fine, and now we say continue, and then OK. So let's zip quickly down, and I suggest you always do this, zip quickly down to the plots. Let's try and work out what's going on. Which one of these works best? Well, for me, there's one here which has the shapes as the lines, and the professions as the kind of marks across the bottom here. I can't really get my head into that because it's difficult to describe. For some reason this one makes sense to me more. So in this case we've got the lines actually represent professions, and the shapes actually represent lines across the bottom. Remember, rectangle is 1, oval is 2. So what does this seem to suggest? Well, I hope you can all see what kind of a relationship is going on here. It looks very much like an interaction, very much like the interaction in the between subjects design when we had psychotherapy and sex of participant. It's a crossover interaction. So some of the professions are doing really good at some of them, apparently, and poorly at other shapes. Some of the other profession is doing well on some shapes and poorly on others. In this, big is better. So the bigger the number up the right hand side here of the y-axis, if you need to remember how to remember y-axis, then I always use the kind of little mnemonic y's up, because y goes up, it's vertical. That helps me remember. But let's have a look here. So let's look at psychologists. They're the blue line. Now, one's a rectangle, so it seems psychologists are better at identifying rectangles than they are at ovals. Okay, that might surprise you if it was a real effect. I'm sure these data are made up, but it might surprise you if it was a real effect. I don't quite know why. Sometimes circles seem more human and squares seem to be more kind of engineering, but that might just be my prejudice against geometric shapes. And contrary-wise, if we look at the engineers, they seem to be better at ovals, which isn't too variable, and worse at rectangles here. So a crossover interaction. Just a note about this, why I said remember it. Unfortunately, you have to remember that you put rectangle as 1 and oval as 2, because silly old SPSS doesn't actually label them appropriately. You have to remember the numbers. So what we might expect to see, though, is possibly a significant interaction, possibly no main effective profession. Main effective profession would be this number, for psychologists, would be this number here at the bottom right, added to this number here, and divided by 2. So it's simply the mean of the psychologist's overall score, irrespective of which shape they're looking at. The main effect of engineers would be exactly the same. This number here added to this number here, divided by 2 to find the mean. So you'd be simply comparing the mean for psychologists against the mean for engineers, and there might be a slight difference there, but it looks kind of pretty similar. With crossover interactions, often there is no main effect. And the same with shapes. This is the average. This plus this divided by 2, find the average, would be the average performance for rectangles, and this plus this divided by 2 would be average performance on circles. So again, possibly not an effect there. So let's zip up to the ANOVA and see what the ANOVA actually tells us. If we can find the ANOVA. First of all, here we got Mockley's test, again, for sphericity is non-significant, so the data are fine. There's no difference, there's no significant difference in the variance across the 4 conditions. So we can look at the within subject effects. We can assume sphericity, so we can read this top line here, because Mockley's test was non-significant. So sphericity assumed, well, there's no significant effect there. and a very small effect size. You don't need to report effect size if the data are non-significant, because they're non-significant. We don't treat it as an effect. You only need to report effect size usually if you found a significant result and then you want to see how big it is. So like, if you like, the first step you have to get over is significance. The second step, then you might want to report effect size. So no effective shape. But there is a shape by profession interaction, just 0.049, which just scrapes below the criterion for, or above, whichever way you want to think of it. It's slightly lower than 0.05, so that we might want to say that that interaction is significant. Where's the between subject effects? Well, SPSS very handily plonks it down here. Again, we find no significance here. In Levine's test, this is looking at the difference in the between subjects variable to see if the variance is approximately the same in those two conditions. So we're all fine to do this. And here are our between subjects effects. Profession here. So tested between subjects effects we're looking at here. Here's profession, and we find there is again no significant difference there. F of 0.001, that's F not P, with the p-value of 0.9, so it's practically nothing. No difference there at all. Effect size is 0, hardly we're talking about. But that's a bit strange. So okay, so we found a significant effect. So what we want to do now is to let's do the simple effect. So we want to see whether there's any significant differences between the individual data points. We're doing pairwise comparisons for each of the possible combinations. So that'll be 4 pairwise comparisons we're doing. So what we do here is we go to compare means, and we'll do the within subjects one first. So we're doing a paired sample t-test, and we simply want to see whether there's an effective shape. So are rectangles overall, irrespective of condition, are they better than ovals, or ovals better than than rectangles? So this is, so we get again rectangles versus ovals. Ignoring the participants, we find there's no main effect there of rectangles versus ovals. And if we want to do compare the two professions, then we need to do an independent samples t-test. We've only got one between subjects variable here, so we don't need to split the file. You only need to split the file when we have more than one between subjects variables. Okay, so we put profession in the sorry, there we go. Rectangle and oval as a test variables. A profession as a grouping variable. Now this has been set rather than 1 and 2. This has been set as 0 and 1. So we need to remember that. Put those in there. And click OK. I will pause it there for a minute and do another recording of this part 2, because we're coming up to the limit. So